In this video, we're going to continue with predicate logic. We're going to either prove or disprove some well-formed formulas. So the first example here we have either prove that the well-formed formula is valid argument or give interpretation in which it is false. So first thing you do, you read it and see if it makes sense or not. There exists some x that will make a of x true and b of x true. Okay, and if this hypothesis is true, this implies that there exists x a of x and there exists the same x that make b of x true. Okay, so it looks like it is valid and we're just going to try to prove it. So number one here, we're going to write the hypothesis that there exists x a of x and b of x, both of them are true. And this is the only hypothesis. So from here we're going to do existential instantiation. That means strip off there exists and what we have left, a of x and b of x. You see how that variable x that exists, I kept calling it x because my conclusion dealing with the same x. And now we could use simplification because both of them are true, a and b are true. I could say either a of x is true because 2 simplification. Also b of x is true from 2 simplification. So each one of them are true for the end to be true. So now I stop and think, here's my goal. My goal is to prove that there exists x, b, a of x, and there exists the same x, b of x. So since a of x and b of x are true for that x, so 5 I'm gonna use generalization. So I'll take 3 and I do existential generalization. That means insert back there exists x a of x and then there exists x b of x, and the same way I would say number 4 e.g., which is existential generalization. So we're just gonna connect both of them and that's our goal. So we use 5 and 6 connection. And this is how we prove that this valid argument is valid. The next example here we have the same way, either prove or disprove. So we're gonna read it and see if it makes sense. There exists x p of x and there exists x for that same x there exists y, that there is a relationship qxy. If these two are true, this will give us the conclusion that there exists x. For that x there exists y, and p of x and q of x is true. So here is the troublesome. I see it's not going to be valid because of this and. There is more restriction here for the same x, and you have there exists some x that will make there exist y, and makes p of x and q of xy both are true. So if we let the domain be all integers, so let's do this. So here we're gonna let the domain to be all integers and we're gonna make p of x is even. So there exists an integer that makes p of x even. And there exists x, there exists y, and the relationship between x and y, let's make it x equal to y plus 1. So here I choose this because I see it's gonna give me an impossibility here for conclusion. So what is the conclusion? Conclusion is that there exists x, there exists y, p of x, and q of xy. So this one x even, and right here q of xy, meaning if you look at it by giving q of xy as 2y plus 1, then it tells me that x is odd basically. So there exists x and there exists y corresponding to that x that makes both x even and odd. That it's impossible. So here we have a contradiction since x cannot be odd and even at the same time. So this argument is invalid. So let's see this example here. Either prove that the well-formed formula is valid argument or give an interpretation in which it is false. So again, what we have, for any x, there exists some y. And there is some relationship qxy. If that's for any x, there exists y. That implies that for any x, that relationship x qxa that exists some value a, that makes that relationship between x and y true. So let's see an example. What should we make qxy? If we let qxy be maybe x plus y equals 0, okay? So here we are saying for any x there exists y, so that for if I add them, they are opposite, x are integers again. So if I add two integers, I get a 0. For any x like 100, there exists a y, maybe negative 100. So x plus y equals 0. So is this would give me a conclusion that for any x, if I take x plus a, I get 0. A is fixed. No. So a is a constant, a is fixed, so this is not true, and therefore not true. Not for every x there is a, and a is a constant here. So it's not true, and therefore this argument is not valid. So the next thing, we're going to go over some old verbal argument. So the Greek philosopher like Aristotle, that lived from 384 to 322 BCE, studied under Plato and tutored Alexander the Great. His studies of logic influenced philosophers for hundreds of years. His four perfect, and here I'm going to go over only two examples, syllogism, are identified by names given by the medieval scholars. So for each formulate the argument in predicate logic notation and then provide the proof. So we're going to go over two of them. One of them is called Barbara, and it says all M are P and all S are M, and therefore all S are P. So again, we are taking from the domain the whole word. For example, all men are mortal, or Americans are men, and therefore all Americans are mortal, if that's the case. Okay, that's an example. So let's write it as an argument, like with predicate logic. So as we've seen in previous section, all M are P, that means for anything, all x's. If it is an M, therefore it's a P. And the same way all S are M. So this is the hypothesis. Therefore, my conclusion is that all S are P. For anything, if it is an S, therefore it's P. Well, we could see this is obvious, so but for all that exists, how are we going to prove this? So first of all, I'm going to need to prove the write down. So first we're going to write down the hypothesis. So here is the first one. And the second hypothesis we have, so here are the two hypotheses. All x, M of x implies P of x, and for all x, S of x implies M of x. And now, the same way we were talking about earlier, we're going to use instantiation, but we have universal instantiation, universal for all. So we strip that quantifier and we end up with M of x implies P of x. So we'll do the same for 2. And then we're going to end up with S of x implies M of x. So what we did, we remove the quantifier using universal instantiation. And now what can we see? S implies M, M implies P. So the conclusion is S implies P. And how you do this? This is HS, hypothetical syllogism, as we've seen in the other sections. And now, as you see, my goal is to have for all x, S of x implies P of x, and this is where we need to reach, and we did by using universal generalization from the fifth step. So this is Barbara. The second one here is called Celarent, and no M are P, all S are M, and therefore no S are P. An example would be no reptiles have fur, all snakes are reptiles, and the conclusion no snake have fur. So let's write down the argument. So the argument no M are P, that means for all X, if it is M, then it is not P. Okay? My second hypothesis, all S are M, that's simple. We say for all X, right? If it is S, that means it's gonna imply M. So these are my both hypotheses. Then my conclusion, I'm gonna write it under here. No S are P. So if anything, if it is S, then it would not be P. And that's the argument we need to prove. So first thing, we write the hypothesis for all X, M of X implies not P of X, meaning no M are P. And for X, S of X implies M of X, meaning all S are M. And now we have to strip the quantifier. So for example, the first one, UI, it's gonna lead me to M of X implies not P of X. And for number 4, I will strip the other quantifier, and I end up with S of X implies M of X. And now what can we say here? Again, the same like the previous example. 3, 4, hypothetical syllogism. And we end up with S of X implies not P of X. And because of this is what we needed as a conclusion. So all what we need is to insert back the quantifier. And then 5, universal generalization. And that's our goal, and we reach it right here. And this is it. This is how we use predicate logic. I hope this is helpful.